In this video, we'll go through question 12 from the 2017 HSC Mathematics Extension 1 exam. Part A. The points A, B, and C lie on a circle with center O, as shown in the diagram. The size of angle AOC is 100 degrees. Find the size of angle ABC, giving reasons. Okay, so here's our diagram, and we're given, in the question, the value of an angle at the center of a circle. Now, when we're given the value of an angle at the center, that should, or perhaps we need to find the value of an angle at the center of a circle, that should kind of suggest that we need to use the idea that the angle at the center is equal to twice the angle at the circumference. Okay, that's one of our theorems, one of our circle geometry theorems. So, how can I involve an angle at the circumference? Well, it can't be angle ABC because these they are subtended by the same chord AC or same arc AC, but they're not in the same segment. So remember, that theorem only applies when the angle at the center and the angle at the circumference are in the same segment. So what I should do is I should pick a point here and call that point D and construct AD and DC. Okay, and now I can see that this angle in here is applicable for this theorem that we're going to use. Okay, so I can say construct the point D on the circumference as in diagram. That's probably the best thing to say, as in diagram, or as in the diagram. I'm just being lazy with my English here. So construct the point D, and then what do we know? Well, we know, firstly, before we apply that theorem, we also have the fact that ABCD is a cyclic quadrilateral because all the points lie on the circumference of a circle. So I can say that ABCD is a cyclic quad, and this is going to come in useful soon. Okay, so now I can go ahead and apply that theorem that I was just saying. The angle at the center is twice the angle at the circumference. So we can say angle ADC is going to be 1/2 of angle AOC, and we have to give the reason, which we just said. The angle at the center equals twice the angle at the circumference. Okay, if you're in an exam, I would suggest writing that out in full and not being lazy like I am. Okay, so that means it's equal to 1/2 of 100, which is 50. Beautiful. So we have the value of this angle here. And now we can work out what angle ABC is, because ABC and ADC are supplementary. The reason they're supplementary, or the reason they add to 180 degrees, is because they're opposite angles in a cyclic quadrilateral. So therefore, angle ABC equals 180 minus angle ADC, opposite angles in cyclic quad. You could probably also say add to 180 degrees. Okay, so that means it's equal to 180 minus 50, which is 130. And that's your final answer. Question B, part I. Carefully sketch the graphs of y equals the absolute value of x plus 1 and y equals 3 minus the absolute value of x minus 2 on the same axes, showing all intercepts. Okay, so we want y equals the absolute value of x plus 1 and y equals 3 minus the absolute value of x minus 2. Let's have a look at the first one, because that involves just a little bit less. So y equals the absolute value of x plus 1. So whenever we're graphing absolute value functions, it's always good to have a look at what the function would look like without the absolute value. So this is just a straight line which has y-intercept of 1 and gradient of 1. So that's not too difficult. That would look like this, and then it would go below the x-axis. But we know that when we take the absolute value, all that does is reflect anything that's negative through the x-axis and flips it into the positive version. So that means that we would have this happening. Okay, and we get this little V shape here. and this is obviously -1, and this is 1. Okay, so that one, there's not too much to it. Now, the second one, y equals 3 minus the absolute value of x minus 2. So here there's a little bit more going on. What we're going to start with, in order to look at this, is we're going to start looking at y equals x minus 2 first. Then we're going to look at y equals the absolute value of x minus 2. Then we'll look at y equals minus the absolute value of x minus 2. And then we'll look at 3 minus the absolute value of x minus 2. So what I'm actually doing is I'm kind of working backwards from where it starts with, and then applying all the things I need to get to what I want to graph. Okay, so we're going to actually do this one on the side, and then once we've got the final thing, add it onto our final answer. Alright, so let's just draw something very rough here. Okay, so we're going to start with x minus 2. That's the same idea, it's just the y-intercept is -2, and I still have a +1 gradient, so that'll look something like this. So that's y equals x minus 2. Then I want to obviously flip that, or anything that's negative, I want to flip it over into the positive across the x-axis, so that I'm applying the absolute value of x minus 2 now. So that'll look like this. That should technically be 2 here, and that should be 2. Okay, and now, so that's this bit here. Now let's have a look at this bit here. What does this do? If I multiply everything by -1, that means every y value takes its negative value. So that means that everything gets flipped across the x-axis. So then I'm actually looking at this. And finally, when I add 3 to this, so if I add 3 to my red curve, I actually get this one here that I've marked in black. So that's just shifting the y value of everything by 3. I'm adding 3 to the y value. So that means everything gets shifted up by 3. And so I end up getting this. Okay, so this point here would be 3 and 2, and this intercept here would be 1. This one here would be -1. Okay, so let's go and add that onto our final answer. So firstly, actually, let's label this x plus 1. Let's use blue to draw y equals 3 minus the absolute value of x minus 2. So we know that it's going to pass through the point 3, 2, which is exactly this point here. It's going to go down across this line, actually. So it's actually intersecting with this thing. They're crossing, overlapping. Okay, this would actually be crossing at the point 5. Okay, now it's good to label all these points here, so the marker knows that you know where everything is crossing. Okay, and of course label this 3 minus the absolute value of x minus 2. Okay, all right, and that's part I. Now the next part asks us to use the graph, or using the graphs from part I, or otherwise, find the range of values of x for which the absolute value of x plus 1 plus the absolute value of x minus 2 is equal to 3. Okay, so we want the absolute value of x plus 1 plus the absolute value of x minus 2 to equal 3. So this is an interesting one as well. But the question gives us a hint. It says using the graphs from part I. So we need to look at these two graphs, our blue one and our black one. Now we can see that these absolute values they're just coming from what we've graphed. Okay, so let's quickly write down what we graphed again. Y equals x plus 1 and y equals 3 minus x minus 2. That's an absolute value. Okay, so if I rearrange this equation here, let me write it in the following way. X plus 1. Now I'm actually going to move the x minus 2 to the other side. And the reason I do that is because now I can see that the left-hand side is my first graph and the right-hand side is my second graph. So when I'm actually solving this start equation, what I'm really doing is seeing where these two graphs intersect. And we can see very clearly from our graph that they intersect when x is between -1 and 2. Okay, so therefore you can say from the graph, x has to be between -1 and 2. And that's all there is to that question. It's only worth 1 mark. So even if you just looked at the graph without stating anything, and you just gave the answer, you'll get the mark for the answer. But it's best for you to write at least something like what I've written here in order to show the marker that you know what you're doing. Part C. The region enclosed by the semicircle y equals the square root of 1 minus x squared, and the x-axis is to be divided into two pieces by the line x equals h, where h is between 0 and 1, not including 1. The two pieces are rotated about the x-axis to form solids of revolution. The value of h is chosen so that the volumes of the solids are in the ratio 2 to 1. Part I. Show that h satisfies the equation 3h cubed minus 9h plus 2 equals 0. Okay, so here we have the diagram, and I've labelled the two areas as A1 and A2. Now, we're told that these areas are rotated to form solids of revolution, and that the volumes of the solids are in the ratio 2 to 1. So that means that the volume of the first one divided by the volume of the second has to be equal to 2 over 1. Okay, that's just basic ratios. So we need to work out expressions for the volumes. So the first one, V1, is obtained by rotating A1, the area A1, around the x-axis. So we know that volume is given, when we're rotating about the x-axis, is given by pi times y squared dx between our two bounds, a and b. So if y equals the square root of 1 minus x squared, well, obviously y squared is just going to be 1 minus x squared. So we have pi times the integral. Now I'm going from -1 to h. -1 to h here. And our y squared is 1 minus x squared dx. And so this is just quite a simple integral here. Pi times x minus x cubed on 3 between h and -1. If we sub those in, what do we get? Alright, so I have pi times h minus h cubed on 3, and then that's going to be minus -1 minus -1/3, so plus 1/3. So I have pi times h minus h cubed on 3, and then -1 plus 1/3 is minus 2/3, and then I have to subtract minus 2/3, so that'll be plus 2/3. And let's just make a common denominator of 3 here. That's going to be beneficial for us. So that'll be 3h minus h cubed plus 2. Okay, so that's the first volume. Let's do the second volume on the side here. Pi times the integral. Now this one's going from h to 1. So from h to 1 of 1 minus x squared dx. Now this is exactly the same integral, just different bounds. X minus x cubed on 3, -1 to h. Okay, we sub in h first. Why have I put, see, I've just looked at the other one, that should be h to 1. Okay, so subbing in 1 first, I should say. 1 minus 1/3 minus, subbing in h gives us h minus h cubed on 3. So this is pi times 2/3 minus h plus h cubed on 3. Okay, it's just algebra, and again we'll make a common denominator. Pi on 3 at the front, this will be 2 minus h plus h cubed. Okay, good. So we've got expressions for v1 and v2. That should be v2 there. And we know that v1 divided by v2 is going to be equal to 2. Or in other words, v1 equals 2 times v2. Okay, and what does that give us? If we sub all that in, we have pi on 3, 3h minus h cubed plus 2 equals pi on 3, now I need to multiply this by 2, of 2 minus h plus h cubed. Okay, we can cancel our pi on 3 here and a pi on 3 here. And we can distribute that 2 through on the right-hand side. So we get 4 minus 2h plus 2h cubed. Okay, that's equal to 3h minus h cubed plus 2. Bringing everything over to one side, let's bring it all to the right-hand side. We get 0 equals 2h cubed plus h cubed is 3h cubed. Minus 3h minus 2h will be minus, that should be a 3 up here. That's why I've made a mistake. That's a 3. So then this actually becomes a 6. So I have 3h, when I bring that over, it'll be minus 6 minus 3, which is minus 9h. And then 4 minus 2, which is 2. Okay, and that's our equation. That's what we wanted to get. Okay, and the next part says, given h1 equals 0 as the first approximation for h, use one application of Newton's method to find a second approximation for h. Alright, so this is the equation that we got from the previous part, and we want to solve that equal to 0. Now we need to use Newton's method. So let's say let f of h be equal to the left-hand side, 3h cubed minus 9h plus 2. And they said that h1 was equal to 0 was our first approximation. Okay, and then the Newton's rule, what does Newton's rule say? It says the following. The next approximation, h2, is going to equal h1 minus f of h1 divided by f dash of h1. So the derivative, f dash or f prime. All right, so we have to work out firstly we have to work out what f prime is equal to. We have to find the first derivative, and then we have to substitute in h1 equals 0 for both the function and the derivative. Okay, so if we differentiate this, it's not too difficult. F of h is f dash of h is equal to 9h squared minus 9. Okay, and it's very easy to read off what f of 0 is and f dash of 0. It's just the constant term in these. So therefore h2 is going to be equal to 0 minus f of 0, which is 2, divided by f dash of 0, which is minus 9. So I have minus 2 over minus 9. That's going to be equal to 2 on 9 as our second approximation. Okay, and that's the end of that question. Okay, part D. At time t, the displacement x of a particle satisfies t equals 4 minus e to the minus 2x. Find the acceleration of the particle as a function of x. Okay, so here's our function which relates the time to the displacement. Now we want to find the acceleration of the particle, but not as a function of t, which is what we usually see it as. We want to find it as a function of x. Okay, so that makes me think that I want to use something, some formula which has x and acceleration in it. And the only thing that I can think of off the top of my head, or the first thing, is d dx of a half v squared. Okay, so if I can work out what the velocity of this particle is, and I can get that in terms of x, then I can apply this and get the acceleration. Okay, so now the question becomes, how can I find the velocity? Well, we know that the velocity is equal to the first derivative of x with respect to time. Now, the problem with doing this is that when we do this, the velocity is going to be in terms of t, not in terms of x. But what we can do is that we can think of this as 1 over dt on dx instead of dx on dt. Okay, so we've just taken the reciprocal of a reciprocal here. And now we can find dt on dx by just differentiating the equation that we're given. So dt on dx is differentiating this with respect to x. The 4 goes, and we get minus 2 times minus e to the minus 2x. Okay, and of course that's minus 2 times minus 1 is just positive 2 e to the negative 2x. So now I have dt on dx, which means that the velocity, which is equal to dx on dt, is going to be the reciprocal of this, 1 over 2 times e to the minus 2x. Now, of course, e to the minus 2x on the bottom becomes e to the positive 2x on top. So I'm just left with a half, and looks like my pen's run out. Nope, it's back. A half e to the 2x. Okay, so here I have my velocity. So now I'm going to apply acceleration equals d dx of a half v squared. So I have the derivative of a half times the velocity squared. So that means I'm going to have a half e to the 2x squared. So this will be d dx of a half times a half squared. So a half times a quarter, which is an eighth. And then just applying our power rules, this gives us e to the 4x. If we differentiate this, we bring down the 4, and so we get 1 on 8 times 4 e to the 4x. And so this simplifies to a half e to the 4x as our acceleration. And here we have the acceleration in terms of the displacement x. And that's the end of that question. Part E. Evaluate the limit as x approaches 0 of 1 minus cos 2x all over x squared. Alright, so here we have a limit question, and it involves a trig divided by an x, or some power of x, essentially a polynomial. So that makes us think of two possible limits that we've studied. Those would be the limit as x approaches 0 of cos of x divided by x, and that's equal to 0. And we also have the limit as x approaches 0 of sine of x on x, and we know that that's equal to 1. Okay, these are our small angle results. Okay, so somehow I need to try to work these into my question here. Now I can see that I've got a cos 2x here, but that's not exactly going to guarantee that I'm going to use this equation here. And the reason is because the argument of the cos function is 2x, and I don't actually have a 2x in the denominator. Now what I could do is I could multiply the denominator by some sort of constant. So in this case, probably 2 or maybe 4. You could maybe think about why I would multiply by 4. And then also multiply the top by the same constant. But that's also not going to work because the top is cos x raised to the power 1, or the cos function raised to the power 1, but the denominator is actually squared. So we either have to have all of it squared or none of it squared. So that doesn't tell us to straight away use this one. So I still have to think, what are some other things that I could do? Well, we have cos of 2x, and we do know some formula, or a formula for cos of 2x. That's our double angle result. So we have cos of 2x is equal to, now before I said there are some formulas because we can actually rewrite the one formula in a couple of ways, but the formula is cos squared x minus sine squared x. And you can see that this is sort of getting there. It's getting better because now I've got some trig functions where the argument is just x and it's also being squared, which is starting to match what we have in the denominator. Okay, but it's still not going to be useful because we still have this 1 lurking in the top. But like I said earlier, and I repeat it again, there are actually other ways that we can write this formula. Okay, there's actually 3 ways in which you can write the cos, the double angle for cos. We can let cos squared x equal to 1 minus sine squared x. And if we do that, we get 1 minus 2 sine squared x. Or we could let sine squared x equal 1 minus cos squared x. And if we do that, we get 2 cos squared x minus 1. Now, this is the one that we're going to use, and that's because we have a 1 minus 2 sine squared. We have this positive 1. And since I'm subtracting cos 2x, I'm going to get 1 minus 1, and that's going to cancel that out in the top, which is going to make things really nice. So we're going to get limit as x approaches 0 of 1 minus, and then I'm going to substitute in 1 minus 2 sine squared divided by x squared. So we have the limit as x approaches 0 Now these 1's will cancel and I'm left with positive 2 sine squared x divided by x squared. Now the 2 is just a constant, I can bring that out the front, and I have the limit as x approaches 0 of sine x on x all squared. And now here, this is going to actually be equal to the limit as x approaches 0 of sine of x on x all squared. We know that this limit from this bit here, the double star, is equal to 1, so it's 2 times 1 squared, which is just 2. Okay, and that's the end of that part and the end of question 12.